Hello, this is Scott Moore from Eljen Corporation. I am the Technical Development Lead, and today I will be going over the Eljen GSF approval in Montana. Before I get started, I do want to go over the DEQ4 because a lot of people have been asking if we were on the approved list. There is a provision in DEQ4 section 6.1.4.3 says that systems that provide documentation or demonstrate through a third independent party that the unit is able to meet the testing criteria and performance required for NSF Standard 40 Class 1 certification or meet the testing requirements outlined in ARM 17-30-718 for 30 milligrams per liter of BOD5 and 30 milligrams per liter of total suspended solids only may utilize a reduced absorption area in accordance with the following criteria. A. For subsurface absorption systems constructed in soils with percolation rates between 3 and 50 minutes per inch, as described in Chapter 2, Appendix B, the final absorption area may be reduced by 50%. Section B. For subsurface absorption systems constructed in soils with percolation rates between 51 and 120 minutes per inch, as described in Chapter 2 and Appendix B, the final absorption area may be reduced by 25%. And that's where the GSF comes in here. So today I will be reviewing company history, the science behind the system, how the GSF works, the GSF sizing options, the approved installation types, and installation procedures as they pertain to the Montana DEQ4. Eljen was founded in 1970 by Joseph Glasser. Joseph is a World War II veteran. He was a navigator on a bomber. He was shot down once in Germany and once in France. He's still alive. He's no longer active in the company. He started early employment in the 80s with the GSF. In 1970, when he started the company, he made prefabricated drainage product out of his basement in his home. Currently, we have over 100,000 systems installed worldwide. We're in every province of Canada, Australia, Sweden, Tasmania, and Puerto Rico. Some of the scientific studies behind the GSF. Croft in 1977 did a study that biological soil clogging is caused from septic tank effluent. And then also in 1977 he teamed up with Lack and Healy. Now Rain Locke actually is the designer of the Eljen GSF. They determined that the biological clogging will define the absorption rate. Then in 1995, Locke discovered that geotextile fabric will improve your absorption rate because that fabric will build up a biomat and will stop the suspended solids from going down to the soil pores and clogging them. Dix in 1999 also did a paper that says sidewall and bottom area accept effluent. And then Tyler, Converse, and Keys in 2001 did a paper on loading rates for highly pretreated effluent. And they also developed the Tyler chart. And what it said in there was that the pretreated effluent can be absorbed by the soil at a faster rate than effluent that is not pretreated because it does not contain the suspended solids. Heavy loading of the soil with liquid effluent can cause saturation in the soil. Long-term soil saturation, everybody knows, will reduce the aerobic activity, and that reduction in aerobic activity will prevent the natural breakdown of the organic material. Suspended solids in the effluent will clog the soil pore structure, reducing the long-term acceptance rate of the soil. On the left, we can see a comparison of the anaerobic bacteria to the aerobic bacteria. The aerobic bacteria, if you were to look at actually both of these under a microscope, the anaerobic bacteria, you don't see a lot of movement. It might twitch or move a little bit side to side, whereas the aerobic bacteria will always be moving around under the microscope, darting back and forth. It's better at breaking down the human waste, but it requires oxygen. It also helps us keep the biomat to a manageable level inside the GSF. So how does the GSF work? There's one piece of continuous fabric that loops up and down over plastic cores. There's 65 square feet in one A42 module. When the effluent is dispersed over the top of that geotextile fabric, it filters out the suspended solids. It also builds up a biomat on the fabric, and the biomat acts as an added filtration system and also processes all the pathogens. Once the effluent flows through the GSF and flows down through the sand, the GSF module itself becomes aerobic, and that's where we get our aerobic treatment, and that's how we are able to manage the biomat formation inside the module so that it doesn't get so thick that it clogs, but is thick enough to filter out suspended solids and also process any pathogens. The drawing down below is an actual drawing from Rain Locke. What he did, he was sitting down at his desk one day and he asked himself, how can I get more surface area into a 3-foot wide trench opening? So he made these little drawings, and the numbers below correspond to gallons per linear foot. So the increases in the surface area with each system, that's what's really important here. It's not so much the geometry of the product. We want to increase the surface area and number of biomat growth zones. The areas where you don't see effluent on the far right are areas that are lined with plastic corrugated material that act as open air channels within the modules to help support aerobic activity. As mentioned in the previous slide, the geotextile fabric provides the primary stage for treatment because it provides a surface area for biological development of the biomat. This promotes the biomat growth away from the soil interface and preserves the unit sand interface by minimizing clogging, and it promotes an unsaturated flow. Because the sand is surrounding the module, it's going to allow the effluent to flow out through the module at a certain pace. So whether you have a fast soil, it will allow the effluent to flow out and still get treatment. And if you have a very tight soil, it allows the effluent to flow out at a rate that will not saturate the soil. One simple way to explain the operation of the GSF is to look at a pier pylon. Notice where the pier pylon starts to decay, in between the low tide and the high tide levels. That's exactly how the GSF system works. Imagine that the pier pylon is the vertical area inside of the GSF module made up of the geotextile fabric. A high tide event would be dosing from the septic tank. It'll fill the GSF module up as it slowly lowers to the low tide level. When it empties out and the effluent has traveled through the sand, now the GSF becomes an aerobic treatment zone. The aerobic bacteria comes in there and begins to eat all the organic deposits that were left from the effluent. The biomat contains all of the suspended solids and processes the pathogens. This picture represents the biomat growth in a stone and pipe system. Once the effluent leaves the pipe, it drains out through the stones with all the suspended solids. Those suspended solids in turn go into the soil pores. They get wet in there, they expand, and they start to clog those pores. As those pores begin to clog, you end up having your effluent stay up in your stone longer and longer. Then you begin to develop biomat on your sidewalls, which eventually will lead to clogging. This picture represents the biomat growth in a GSF system. The effluent flows out of the distribution pipe on the top of the module, flowing through the geotextile fabric. The geotextile fabric, in turn, builds biomat, trapping suspended solids in the biomat. Once the effluent drains out of the GSF module, the module becomes an aerobic treatment zone, and the aerobic bacteria will keep that biomat at a manageable level. anything that does make it through the biomat will get trapped in the sand layer. We use ASTM C33 sand below and around the GSF module. Once that sand processes the effluent, that also becomes an aerobic treatment zone, minimizing biomat development in the sand layer and preserving your soil layer and increasing your long-term acceptance rate. Here are two trench installation types. On the left, you can see a curved system. It's actually more of a zigzag, and on the right is a straight trench. The picture on the left was on a lake lot in Wisconsin. There were two lots close together, and the lot where we had to put the system in, the homeowner tore down the original home, put up a new home, larger home, garage, wanted to put a pool in. There was nowhere for the septic system. So he didn't want to remove any trees, but we were able to put it in the front yard in between his driveway and his neighbor's driveway that both S'd into their property. They curved in the shape of an S. We were able to zigzag the septic system between the driveways and meet all the setbacks and still have a septic system in place. Here's a cross section of the trench. You can see we have 6 inches of sand directly below the modules, and we also have 6 inches wide, 7 inches high of sand going up even with the top edge of the modules. The vertical separation is according to the circular DEQ4 to restrictive layer, and that is measured from the bottom of the sand. And we require a minimum of 10 inches of cover material over the top of the module, or 6 inches over the pipe. If you had to do more than 18 inches over the top of the module, we require venting, or if the material that you're putting on top of the module will restrict airflow, then we require venting. Here is a plan view of the system. 3-foot minimum separation from edge to edge of native soil in between trench rows, if pressurized, is required according to DEQ4. You can see that you have the module 2 feet wide, and then the 6 inches of sand on either side to make it a 3-foot wide trench. In-ground beds are also allowed. When installing an in-ground bed, you do not require to have 3 feet of naturally occurring soil in between the rows. The minimum we require is 1 foot of C33 sand in between, because if you install the modules at 2 feet wide with a minimum of 6 inches of sand on either side, when you place 2 of them side by side, you will have 1 foot in between. This one shows a pressurized system that is going to utilize orifice shields. Eljen recommends putting the low pressure pipe inside of a 4-inch perforated pipe. Here is the bed cross section. You see we still require a minimum of 10 inches of cover, 6 inches of sand below. The modules are centered inside the bed when making a bed design. Mounds or above grade systems are also approved. You can do straight systems or contoured systems. Here is the cross section of the mound. The minimum sand requirement will be at dimension D, or whatever is required to meet the vertical separation to the restrictive layer according to DEQ4. The recommended slope on the toe of the mound is a 3-to-1. Here is the mound top view showing all the dimensions. Here is a top view of a contoured mound. And if you notice the areas where there are spaces in between the module, those areas need to have the edges of the module covered with fabric and sand placed in between up to the top edge of the module, making sure that there is no distribution going directly to the sand and that all distribution is over the top of the module. The distribution pipe does not have to be in the center of the module. The way that the plastic core runs inside the module, if effluent is deposited to the left side of the module or the right side, it will fill up the entire module. The distribution methods for the GSF are gravity or siphon dose, pump to gravity, or pressure dosing. When doing a pump to gravity system, Eljen likes to use a D-box. When using a D-box, we like to use an oversized D-box with a velocity reduction. It was difficult to see with the last picture, but what you do is you run your 1.5" or your 2" force main into a 4" pipe that's about 2 to 3 feet long. This will reduce the velocity going into the D-box. If you don't reduce that velocity, that effluent could force its way down one line more than another. The dose rate for the A42 modules are 3 gallons per module per dose, with a maximum of 25 gallons per day. Next, I will be covering the installation procedures for trenches, beds, and mounds. Excavate the distribution cell or area. When doing an above grade or a mound system, the first step would be to remove all vegetation down to the surface level and rake it out of the area. Then do a scarification or chisel plowing, as they call it in some states, of the area to loosen up the native soil. Then install the C33 sand. And be sure that when they're installing the C33 sand that they are driving over the sand so the sand will mix with the native soil. Having a scarification inside the trench or the chisel plowing in the mound is one of the most important steps in this process. Once that sand mixes in with the native soil, it will allow the native soil to draw the effluent out of the sand at a faster rate through what's called capillary action. Rake your sand base level and install the modules end to end with the white stripe up. You can see the white stripe on the left. This is actually what the white stripe looks like. It does not indicate where to put the pipe. It's just showing what side up. If you take a closer look at both of these photographs, you can see there's more fabric visible on the top side with the white stripe than on the bottom side that does not have the stripe. The reason why we want the side with the least amount of fabric to be down is because the areas that will develop the most biomat are areas where you have two wet surfaces together. Having the fabric contacting the wet sand, you will have less oxygen there. It won't be enough to fail a system if they are installed upside down, but it will work better if they are installed correctly. Lay out the distribution network, and it's difficult to see in these photographs, but there is one wire hoop that holds the pipe in place for each module. The wire hoop goes through the module and into the sand about 3 inches so that nothing will move when you're covering your system. Make sure that the ends are capped, otherwise all the effluent will just flow out the back. Here's a drawing of a pressurized system with the ends capped. Just take a hole saw and drill your 1.5" or 2" hole right into your cap and put it on. Should work fine. Here is a drawing of one low pressure venting option. When making a turn up in your GSF system, do not allow the perforated pipe to go out past the edge of the module. It's okay if it's inside a few inches, and then you can run your pressure pipe right up through the top. This installer chose to have a separate low pressure pipe going up for his clean out and a separate vent on the 4" pipe. That's fine. It makes no difference to Eljen. Whatever the installer would like to do, it's all their preference. Here's some venting options. On the left side, it's 2 rows that are sharing a vent in the middle. The right picture, there are actually 4 rows with 1 vent in the corner. As long as there is a vent in there, if you have too much cover material or the cover material will limit the transfer of oxygen, 1 vent should be fine. Once your distribution network and vents are in place, lay the cover fabric down over the center of the modules. To secure the gray fabric, place shovelfuls of sand or topsoil over the center of the pipe and let it drape down over the sides of the pipe. Make sure they do not throw sand up against the side of the distribution pipe because you could block the distribution holes from the pipe. Place the fabric down the sides of the module and then throw sand up against the sides of the module. At no time should any part of the module be contacting the sand except for the bottom of the modules. Once the pipe and fabric are secured and in place, cover and seed. I thank you for your attention today, and if you have any questions on installation procedures or if you would like me to review any plans, please contact me at 203-597-7275 or send me an email at smore@eljen.com. Thank you very much.